Hello, welcome back. So here is our cylindrical apparatus where we have our outside cylinder noted by the solid line and our inside cylinder noted by the dotted line. We have a coordinate system on the lid of the outside of the top cylinder where Z is in the vertical direction, our theta is in the tangential direction of the circle, and our R direction is into the board.
Yeah, so what we're doing here is we're going to be ending up solving for the torque at which we applied to this apparatus to make it spin. But to do so, we need to make some assumptions about what we're doing. The first one is that we have a steady state, that this is a Newtonian fluid, that we have this linear velocity profile we drew up here with the outer cylinder being on the bottom, and then our cylinder being on top. And of course, there's going to be no slip boundary conditions, the walls. And we're going to see from this linear velocity profile that we don't have any velocity in the E theta, or no, we do have a velocity in the E theta, no velocities in the EZ or the R direction. So we can cross those out, and again, like we said, there's a steady state, so there's no time dependency on this either.
Because of our no-slip boundary condition, we can set or no-slip assumption, we can set our boundary conditions for these two. So for when R is at 0, which is on the outside of the cylinder, we can have a velocity and the theta is also at 0. But when our R is the distance on the inside cylinder, it is equal to the velocity of the inside cylinder. And we get our velocity equation in reference to R as a function of R, that it's V times R divided by D. But this V is angular velocity, so we have to multiply it by, or it's equal to omega times big R.
And then we're going to be looking at the shear stress. So shear stress in the R theta, that's just the viscosity of what we used, which is glycerin, times the velocity profile there, which is just, again, omega R. And because this is a shear, it's going to be in the negative direction according to the way the velocity profile is moving. So next, in order to solve for the torque, we're going to need a force. And this force equation is just that shear stress times an area, which is the area of the cylinder. So again, we have that shear equation just times the area of the cylinder. And then we have torque.
Yeah, so to find torque, we have our distance cross product of our force, which is just big R, and then this force equation right here, which we get torque. We have all these values. We found our viscosity online. Here's the reference. Can you see that? Yeah, you can see that. Our distance, our height of our apparatus, the radius of our apparatus, and RPM converted to radians per second instead of rotations per minute. Plug it in, and then you get torque is equal to 11.18 pound-feet.